Review questions for you up on the board to review the major concepts we talked about last time, specifically about imaginary numbers, but also about polynomials. So read through those questions, talk about them with your neighbor, and we'll start in 2 minutes. Oh, and also sign in on the side table there, and there's also 2 new packets for you. Yeah, sure.
I just saw your post.
That's what we talked about.
Okay, because I was
We never talked about it.
okay.
No, it's still it comes really close. It only touches it.
That's what I'm saying.
Okay.
That's why
I'm sorry, and I didn't realize that there was a problem like that again.
okay.
So I need to talk about
No, that's all right. And you could explain also, because I was going through it.
Which one?
You explained to me that it was also, it was 12, yeah, 12. And I really did 5.
Sure. Did you already type that into the analysis and see what the actual answer is?
No,
That would be it, because then that way you can actually see what the answer is.
okay.
And then you'll be able to check to see if maybe it's just the way you typed the answer. I'm not sure.
Yeah, because Friday, they see Terry error, and that's
Well, I'm sorry.
no.
I'm going to point out number 13 today.
Okay, thanks.
All right. Well, good morning, folks. Let's get started. First of all, why did mathematicians invent I is equal to the square root of -1? Why do we even have that terminology? Why do we work with this mathematical object?
So that every equation has an answer?
Yeah, exactly right. So that every equation has an answer. And what we mean by that is, let's say that we have just the simple equation x squared plus 1 equals 0. I'd like to find a number I can plug in for x such that this becomes a true statement. That's always the end game of algebra, is find a number that you can plug into the equation so that it makes it a true statement. And if you only use the numbers on the number line, so if you just look at the number line, the standard number line with positive and negative numbers, there is no number on the number line that will make this equation true. That was dissatisfying to mathematicians. They thought, no, I want every equation to become true if you plug in the right number. And since there are no numbers on the number line that I can plug into here, let's make a new number called I equals the square root of -1, so that when I plug that into the equation, it can make the equation true. And that's ultimately what they wanted, was just for every equation to be able to be true if you plug in the right number. So if you're only choosing from the natural numbers, you know, the regular numbers on the number line, some equations don't have a number that you can plug in to make it true. But if you allow yourself to also consider this as a quote-unquote number, then yes, now every polynomial, you can make a polynomial true by plugging in the appropriate number. Okay, so that's why we invented it. What is I squared equal to? Yeah, just -1. You just square both sides and you get -1. What are conjugates? Specifically, what's the conjugate of 3 plus 2i? The conjugate would be 3 minus 2i. So all you do is you just change the sign in between the real number and the imaginary number. So those are conjugates. And finally, a polynomial of degree 5 might not have 5 x-intercepts. So recall, if you had a polynomial of degree 5 First of all, that's an odd-powered polynomial. So we would expect a n behavior to look like this. And theoretically, it would have 5 x-intercepts. So maybe it would go 1, 2, 3, 4, 5. But it doesn't necessarily have to have 5 x-intercepts. Because if I took the polynomial that made it look like this, and I just shifted it all upward by, say, 10, then now my graph is going to look like this. And there's only 1 x-intercept. So just because your degree is 5, that doesn't guarantee you'll have 5 x-intercepts. You might only have 1. Or in fact, if it's an x to the 6th power, you think, oh, I have 6 x-intercepts? Not necessarily. You could have none, you know, because an x to the 6th would have an n behavior that looks like this. All the wiggles could take place above the x-axis. So you could have none. The power, the degree, is just the maximum number of x-intercepts. You could always have less if you shift your graph up or down. So in any case, it might not have 5 x-intercepts, but what will it have? If you take your polynomial and you actually factor it, you can always factor it into 5 parentheses. You absolutely can. You can factor this into 6 parentheses. You can factor this into 5 parentheses. And if you do that, you're going to end up with your 5 binomials. And what you're hoping for is real numbers in there. And if it is a real number, then it goes to an x-intercept. But let's say you only have 1 real number in there. All the rest of them could be numbers involving I, in which case they're not x-intercepts. But they are nevertheless numbers that you can plug into the equation to make it true. So the answer to the question of polynomial degree 5 might not have 5 x-intercepts, but it will have 5 factors, some of which could be imaginary. So again, if it's a real number factor, it's an x-intercept. If it's an imaginary factor, it's not an x-intercept. But it's nevertheless a number that you can plug into the equation to make it true. Okey-doke. Well, those were just some warm-up questions. Here we are on, what, October 1st? Happy October. Do you find that it's nice and cool outside and you're a little more chipper and happy today? I heard that a hurricane is coming up from the southwest over either the Gulf of Mexico, no, not the Gulf of Mexico, like Baja California or the Pacific, and it's going to hit us by like later today. Did anyone else hear that? I think the word hurricane is a little strong. I mean, what are we probably going to have? A few raindrops. But I'm excited for it. So that should be today sometime. So here we are, October. Happy day. We've got 2 days here that we're going to do chapter 4. And today during our break, I will run over to the photocopy center to get your practice test. And that way, everyone, you'll have all of this week and part of next week to be looking at your practice test. I'll give you the practice test today. I still need to go home tonight, pour myself a nice tall glass of iced tea, and fill out the practice test so that I can post it online and let all of you see the solutions. Because I plan on giving you the solutions for every practice test so you can feel confident. Okay. Hey guys, I like iced tea. What are you laughing at? Okay. All right, so let's see. Let's get started. First, I'll tell you a joke. What do you call a bear without teeth? Some of you have heard this one. What is it? A bear without teeth? I thought someone said it. A gummy bear. That's right. All right. So I'd like to review some homework questions first. I put up 3 questions that I want to do with you. I like the idea of starting class with reviewing homework. So if anybody has homework questions, you can always feel free to do that. Of course, I'm hoping that you're emailing me over the weekend. And I did get quite a few emails over the weekend, and I also got a few forum posts. So folks, just remember when you go into your MORE program and you click on forums, you should click on that because within chapter, where are we, chapter 3? We already have 5 forum posts where people posted questions and then I responded and gave solutions. So definitely be reading those forum posts, just for more tips about how to solve these problems. Okay, so a couple good questions from the homework from 3.2 and 3.3, which is due tonight, so you still have time to go in there and finish a couple of these. Here's number 10. Now, when you look at a problem like number 10, let's do this together real quick. This is a straightforward problem, which we did talk about doing. So we know how to build this solution. We have an x-intercept here, here, and here. This is a slice, that's a slice, and this is a bounce. So I can pretty quickly build my polynomial by just saying I have a constant or a coefficient. So then I have an x-intercept at -3, so x plus 3, at -1, so x plus 1, and at +2, so x minus 2. Now this is a slice, so I just put a 1. But just to preview something, all it really has to be is an odd number. It just has to be an odd number. So I just go with the smallest odd number, which is 1. Likewise here, it's an odd number, so I put a 1, and this has to be an even number, so I put a 2. Technically speaking, I could put a 4 there. I could put a 6, an 8, a 10. It just has to be even. All right, so far this is what we have, but we also have to make the y-intercept work out. So my y-intercept is 0, 3, which means if I plug in 0, I should get -3. So now I'll do that. I plug in 0. 0 is so easy to plug in, I'm not even going to write it down. I mean, 0 plus 3 is 3. 0 plus 1 is 1. 0 minus 2 is -2. And all of that should equal -3. And what I'm doing right now is figuring out my constant, my coefficient. So first you're just writing down a possible formula, and then you're plugging in the y-intercept in order to solve for the coefficient. Now this gives us c times -2 squared is 4, 4 times 3 is 12, so I have 12c equals -3. I'm dividing up to 12, 12. I get -1/4. So now my final answer is f of x equals -1/4 times x plus 3 to the first, x plus 1 to the first, x minus 2 squared. So that's building your polynomial. Let's see if it works. What was that? -1/4, and then x plus 3, x plus 1, and x minus 2 squared. That last one is squared. And there we go, so it worked. Okay, this next one, number 11, I apologize, I did not complete, wait, no, that one is fine. It was number 11, what the heck, it changed it.
It keeps on changing.
Oh, it randomly generated a different problem, that's too bad, because, well, can I ask it for a different one?
If you, I think on the
You have
top,
to just answer it.
Oh, just to answer it?
Yeah, press and just do some wrong.
submit.
Instead of trying to do some.
Oh, great. Ah, there we go. So now this one's different. Okay, that's why I didn't catch it, because when I go through it, I look at all the problems, and it generated a problem that we had solved. This one we have not solved. This is very unique. Look at what is happening there at number 2, at the x-intercept of 2. It doesn't bounce, and it doesn't slice. It doesn't look like a bounce or a slice. A slice is just, straight through, and then a bounce would bounce off. This one looks like it wanted to bounce, like it was about to bounce. It was coming up, and it looked like, oh, I'm about to bounce down, but then no, in fact, in the end, it bounced up. So can you all tell that that looks different as a slice than, say, that slice? This slice goes straight through. This slice comes in horizontally, and then it leaves horizontally. Now, by definition, a slice that goes straight through, you can use the exponent of a 1. So this slice as well, it goes straight through, you could use the exponent of a 1. This slice, because it goes horizontal like that, you have to use an exponent of a 3 or higher. I did not cover that in class because I didn't realize they were going to give a problem like that, because when I went into more, it generated a problem that looked like a normal one. And yet, apparently, it's randomly generating problems like this for you as well. So let's just talk about that. I would start the problem the same way. I'd say f of x is equal to some coefficient times that x-intercept of x plus 4, and then this x-intercept of x plus 1, and this x-intercept of x minus 2. And now this is a slice, so I give it to power of 1. That's a slice, I give it to power of 1. This one is a special kind of slice. It comes in horizontally and leaves horizontally, so I have to give it a power of 3. Now you could ask a really good question right now. Why 3? Right? Why does it have to be 3 instead of 1? And I'll just hint at an answer for you, which is if I had a polynomial of degree 1, like let's just say it was x plus 2 to the first, well, that's technically just the equation of x plus 2, which is mx plus b. And how does a line cut through the x-axis? Straight through, right? If it's to the power of 1, it's technically just a line, that particular part of the equation. And so a line cuts straight through. Whereas if I had y equals x plus 2 to the third, well, you'd have to go look and see what a cubic looks like. What does a cubic graph actually look like? Does a cubic graph slice straight through? Like here's x to the first, it cuts straight through. What does x cubed do? It has that feature of coming in sideways, going horizontal, and then leaving again. And in fact, any power higher than 3 that's an odd number, it has that feature of coming in sideways and then leaving sideways. So if you want it to cut straight through, it's x to the power of 1. If you want it to come in sideways, it would be 3 or 5 or 7 or 9 or any odd number. Okay, well, so let's finish that problem. We're over here. So In this particular case then, since it comes in sideways, it would require an exponent of 3, or 5, or 7, or 9. But you just go with the smallest exponent, which is just a 3. So now I'm ready to plug in my x-intercept, my y-intercept, which is 0, -3. So now I can say if I plug in 0, then if I plug in 0, that's just 4, and that's just 1, and that's -2 to the third. So, and all of that should equal -3. So now 2 cubed is 8. That's actually -8. -2 times -2 times -2 is -8. Times 4 is -32. C equals -3. Oh, is that really right? Yeah, boy, that's correct. It's just not very pretty. So that's C equals 3/32. Everybody's favorite fraction, 3/32. All right, so that's the coefficient that's in front of your polynomial. So now if I write down my final answer, f of x equals 3/32. And notice you need to put that in parentheses. And then x plus 4 to the first, and x plus 1 to the first, and x minus 2 cubed. Let's see if it works. That was 3/32, x plus 4, x plus 1, x minus 2 to the third. There we go. And it worked. So I suppose only half of you might have had that problem because it's randomly generating different problems for different people. You might have had a problem with this strange slice and you might not have. So if you did have a problem with the strange slice, it has to be a power of 3. Okay, does anyone else have any other questions from the assignment 3.2 to 3.3? Okay, so last question I got then was this one, number 13. It says find all the zeros, and that's it. It just says find all the zeros. So presumably you're doing synthetic division. And you would say, okay, let me come over here. I would start by putting down my coefficients, 6, -19, 16, and -4. And I wanted, well, what number should I plug in? They didn't tell me what number to plug in, so I'm going to use Descartes' rational roots theorem and say, well, I need all the factors of 4 over all the factors of 6, which gives me 1, 2, or 4 in the numerator, or 1, 2, 3, and 6 in the denominator. And that is a lot of possible fractions. Right? That's a ton of different possible fractions. So I actually list them out. I get 1 over 1, 2 over 1, 4 over 1, or 1 over 2, 2 over 2, which is just 1, 4 over 2, which is just 2, and then 1 over 3, 1 over 1 again. Wait, what am I doing? I'm on to 2. No, I'm on to 4 now. Gosh, I lost track. So I did 1 over, no. Oh, so I was going way too fast. Let's start this again. I'm actually going to put it in color. I'm going to do 1 over each of those. That gives me 1, 1/2, 1/3, 1/6. And then I'll do 2 over each of those, 2 over 1. So that'd be 2 over 1, 2 over 2, which is just 1, 2 over 3, or 2 over 6, which simplifies to 1/3, so that's already there. And then 4 over 1, 4 over 2, says 4 over 1, 4 over 2 is just 2, 4 over 3, and 4 over 6, which is 2/3. Oh, which is already there, so there we have it. Those are all the different possible numbers that I could try in synthetic division. And at that point, you might say, oh my gosh, where do I even begin? Like, what number out of all that would you want to choose? I mean, maybe 1, because that's the easiest one. But what are you technically allowed to do? You can graph it. And in fact, you can even graph it during a test. If you were on a test and you wanted to, you could just type that all into your graphing calculator. You could see where the x in it. Whoa. I don't know what I just did. Okay, I need to type it in. Gosh. 6, -19, 6, -19. What's the next one?
Plus 16x minus
Plus 16x minus what? 4. Minus 4. Okay. All right, so now by plugging this into my calculator, or Desmos, I can see all my x-intercepts. So now I just know that it's 1/2, 2/3, and 2. 1/2, 2/3, and 2. So now I know it's 1/2, 2/3, and 2. And just by graphing it, that took all the trial and error out of the picture. Now you just know these are the numbers that you need to use. So I'll go ahead and use 2 first. Let me get rid of that graph. There we go. I'll go ahead and use 2 first. So jump to 6. That'd be 6, 12, -7, -14, 2, 4, and 0. Well, that's great. So now I'm down to, I started with x cubed, so now I'm at squared. So now I have x minus 2 is my first factor, and then 6x squared minus 7x plus 2 as the remaining bit. So that's how far I've gotten so far. I started off with this cubic, and now I'm here. And now I need to factor this one, and I already know what my other two x-intercepts are. So I'll do the next easiest one, which is 1/2. So now I can go ahead and do synthetic division with 6, -7, and 2. And this time I'll use the number 1/2, because I already know that's an x-intercept. So now I drop the 6, and so 6 times a half is 3, -4, half of that is -2, which is 0. So now I already had my x minus 2. Now I have my 1/2, so that's x minus 1/2. And now I drop from x squared down to x, and that gives me my last factor, which is 6x minus 4. And there we go. I'm fully factored now. If I really wanted to, I could take a 6 out of this and bring it out to the front. So I'd have 6 times x minus 2 times x minus 1/2 times x minus 4/6, which really reduces to 2/3. So my final form would be 6 times x minus 2 times x minus 1/2 times x minus 2/3. And now you'll actually recognize all of my x-intercepts. My x-intercepts were 2, 1/2, and 2/3. I've got the whole thing factored now. I used my graphing calculator to help me out to get rid of all the trial and error. And let's just see if it worked. That would be, find all the zeros. Oh, I don't even have to factor it. I just need the zeros. Oh, well, then in that case, I mean, if all you need to do is type in the zeros, did I even have to do all that factoring? No, I could have just typed them all in straight from Desmos. Okay. Annabelle, does that answer your question about the roots? Okay. Regardless, it's really nice to know that you can use Desmos to know ahead of time what the roots are, use those numbers to do synthetic division, and finish the factoring. Okay. Well, folks, continue emailing me and sending me your questions. I really appreciate that. Make sure everybody looks in the forums to see that we have quite a few problems already posted in there, so everyone can benefit from that. And otherwise, I think we're ready to go. Not go as in leave, just go as in start the next session. All right, we technically had a little bit left to finish from section 3.4. So please take out your notes for chapter 3. Let's go back to the end of chapter 3. We had only done one problem with imaginary numbers. Let's do, I think, 1 or 2 more that I chose for us. So this is section 3.4. Oh, you're really going to like this. And we had already done number 9, right? Okay. So folks, everything we did in chapter 3 leads up to this moment in this packet, which is the fundamental theorem of algebra. It states that suppose f is a polynomial function with a complex number of coefficients of degree n greater than 1, then f has at least one. Okay, well that's not very exciting. The fundamental theorem of algebra, the way they said it is not very good, is that if you have a polynomial, which is, say, x to the 5th, then you absolutely will be able to factor it into 5 parentheses, some of which are going to be real numbers, and some of which could involve I. But the key thing is you're going to have 5 of them. Then you might not necessarily have 5 x-intercepts, but you will have 5 factors. And what that means is 5 numbers you can plug into the equation to make the equation true. So that's what we're saying here with these 2 problems is find all the zeros of the polynomial, then completely factor it over the numbers and completely factor over the complex numbers. So they just want us to factor this into 3 factors, which is guaranteed by the fundamental theorem of algebra. Even though there might only be one x-intercept, we're going to have 3 factors. So what I did is I went ahead and I took this, and I already graphed it in Desmos, and I found 1 x-intercept, right? Which is what all of you are allowed to do as well. Even during a test, you can use your TI-82 calculator, graph it, find at least 1 x-intercept, and that allows you to begin the process of synthetic division. So everybody, let's start the process of synthetic division. You're going to have your 3, -13, 43, -13, and we're going to use 1/3. Why are we using 1/3? Because I went into Desmos, I graphed this, and I saw that there was an x-intercept at 1/3. So therefore, I know that 1/3 is going to work in the process of synthetic division because an x-intercept 1/3 0, plug in 1/3, I get 0 out. So this might look scary at first. You're like, oh no, 1/3. You can always use the calculator if you like, but you can also just keep in mind divide by 3. That's what 1/3 means, divide by 3. So we drop the 3. 3 times 1/3 means 3 divided by 3, that's 1. And then add, negative 12. Negative 12 divided by 3 is negative 4. Add, that's 39. 39 divided by 3 is 13. Add is 0. So keep in mind, doing synthetic division with a fraction just means divide by. That is if it's 1/3. If it was 2/3, that'd be different. You might want to plug it in your calculator. Okay, so where does that leave us? We started with x cubed, now we're at x squared. And so far, our polynomial is x minus 1/3 times 3x squared minus 12x plus 39. Now, I suppose I should show the graph of this, because the question is, what do we do next? We want to continue to factor that. And yet, if you take your original one, 3x cubed minus 13x squared plus 43x minus 13, you'll see that there is only one x-intercept. That's it. There's just one x-intercept. So what number can we use next in synthetic division? Well, technically nothing. There is no other number. I mean, if we wanted to plug in an imaginary number, that would work, because since there's only one x-intercept, we already now know that the other two factors have to be imaginary, but I don't think anybody wants to plug an imaginary number into synthetic division. Can you imagine, or imaginary, how terrible it would be to do synthetic division with an imaginary number like 2i? Nobody wants to do that, right? So when you get down to a quadratic that doesn't have a real solution, what do you do then? You can try to factor, but it won't factor because the solution is going to be imaginary numbers. So how else do you solve a quadratic other than factoring? The quadratic formula. So that's all you would have to do at this point, is the quadratic formula. So let's try it. We have negative b, I'm going to write down my quadratic formula here. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm going to write it down empty. So negative something plus or minus the square root of something squared minus 4 something something all over 2 something. And so now I plug in all my numbers. So negative b plus or minus b squared minus 4ac all over 2a. So I have all my numbers in now. And now I start to simplify. Negative 12 is 12 plus or minus the square root of, definitely need a calculator for that. Oh, I don't have, oh, I do have a calculator. Who lives home without a calculator? Come on. All right, so now that gives us 144 minus 4 times 3 times 39. Ooh, that's a negative number, negative 324, all over 6. Now, what's the square root of 324? Because remember, how can I simplify the square root of negative 324? What do I do with the negative? Technically, I just bring the negative out, right? So it's the root negative, I'm sorry, it's root 324 with an I involved. And if you do the square root of 324 in your calculator, you'll see it's just 18. So that's actually just 12 plus or minus 18i all over 6. Now what do I do? How do you simplify fractions where you have a single denominator and multiple parts in the numerator? You can just split that fraction into 2 separate fractions. So now I have 12 over 6 plus or minus 18i over 6. That's very convenient because both of those are divisible. So we ended up with 2 plus or minus 3i. So in other words, we have 2 possibilities, 2 plus 3i or 2 minus 3i. Those are the other 2 possible x-intercepts, but they're not really x-intercepts. They're just numbers that you can plug in to make the equation true. So how do we write down our final answer? If the solutions are 1/3, 2 plus 3i, and 2 minus 3i, those are the actual solutions. And if that's all the program wanted from you, that's what you would type down. You would say, those are the solutions. But if you wanted to write an actual equation, like f of x equals, then you always start by writing x minus, x minus, x minus, And then you put in all of those x-intercepts. Well, x-intercepts, solutions. So first I put in the 1/3, and then I put in the 2 plus 3i, and I put in the 2 minus 3i. Oh, you know what? I bet someone can tell me what I did a little inconveniently at the beginning of this problem. What could I have done to my 3, 12, 39? I could have taken a 3 out, and in fact I should have, because the problem is going to be needing a 3 up front in the very beginning. Because technically I could have taken that 3 out, and that would have made my whole quadratic formula a lot easier to solve. Let me show that again, but with the proper synthetic division. If I had taken that 3 out, I would have only had x minus 1/3, and if I took a 3 out, then I'd only have x squared minus 4x plus 13. And then that's going to be much easier to do the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac. What is 4 times that? 52? Yeah. All over 2a. And so that would give us x equals 4 plus or minus, what's 16 minus 52? 36. All over 2, which is 4 plus or minus 6i over 2, which is 4 over 2 plus or minus 6i over 2, which is 2 plus or minus 3i. Okay, so yeah, factoring out that 3 up front would have been helpful to make the quadratic formula easier to do, and in the long run, you need that 3 in front of your answer. So that's your final answer, not forgetting the 3. I'm sorry, folks. I did that same thing the other day where I forgot to factor out the 3. I need to remind myself to look for opportunities to factor out coefficients. All right, well, that's the end of the problem. Questions about that particular one? Nobody's asking any questions. So I think I had one more that I left for us to do before we moved on to chapter 4. Let's see here. Oh, actually, no, there were a couple more problems. My goodness. Let's see. I went ahead and I crossed out number 11, so you can all cross out number 11. Number 12 I left for us to do, so we might go ahead and do that. And then there's a couple other problems here, which are just building functions. Wait. Yeah, because I crossed that one out. Okay, yeah. Number 12. This will be our last example of doing a full factorization of a polynomial with potentially imaginary roots. So, whether you're doing your homework or you're on a test, what's the first thing you're going to do with that polynomial? Graph it. Right? That's the very first thing you would do is graph it, because that way you can see what the x-intercepts are and know what you're doing. So I'm going to go type in x to the 5th minus x to the 4th plus 7x cubed minus 7x squared plus 12x minus 12. Okay. And how many x-intercepts do we have? Well, it looks like 1. Now, you might say, how far out do I have to zoom before I'm confident that the graph doesn't like come back down and touch the x-axis again? But at this point, as we're zooming out, it seems pretty confident that it's just the 1 x-intercept. It's not going to come zipping down and touch it again. So we have the 1 x-intercept at x equals 1. So that's how we're going to begin our synthetic division. So isn't that nice that you're allowed to use your graphing calculator to know what numbers to use in synthetic division? So let's try it. We're starting with our coefficients of 1, -1, 7, -7, 12, -12. And we know from the graph that 1 is going to work. By the way, folks, do we have all the powers of x? X to the 5, x to the 4, x to the 3, x to the 2, x to the 1? No x. Yes, we do. All right, so synthetic division. We drop the 1. So it's 1, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. We started at x to the 5th, so now we're down to x to the 4th. X cubed, x squared, x, no x. And so now we have x minus 1 times x to the fourth plus 0x cubed plus 7x squared plus 0x plus 12. All right, well, that's as far as we know how to go right now. We already looked at the graph. There was only one x-intercept, and that was at 1, and we already did synthetic division with 1. So what do we do with the rest of that? Since we don't have any more numbers to plug into synthetic division, we don't know how to continue factoring it. The first thing we might do is just clean it up a little bit and say x to the fourth plus 7x squared plus 12. And then maybe you recognize that from work that you did in 120 or a previous algebra class. Is that factorable? It looks like something that's factorable, right? Because what multiplies to make 12 that adds to make 7? 4 and 3. So we're really tempted, except what's wrong? It's x to the fourth and x squared. Well, is this allowed to happen? If it was just x squared plus 7x plus 12, we would all jump on that and say, oh good, it factors into x plus 3, x plus 4. Well, right now what we have is x to the fourth plus 7x squared plus 12. So one thing that we could do, and I want you to try this out, is to try substitution. Let's say that you, instead of x squared and x to the fourth, what if we let y equal x squared? In which case, instead of x to the fourth and 7x squared and 12, x to the fourth is really x squared squared, and that's 7x squared plus 12. So now I can replace these x squareds with another variable, y, and just call this y squared plus 7y plus 12. That's called substitution. I don't know if you've seen that technique before, but now that I've replaced my x squareds with a y, I do have something that's factorable, and that gives me the y plus 3, y plus 4, which once I finish solving for y, that would give me, by the zero product rule, y equals -3 or y equals -4, at which point I go back in my substitution and say, well, y was actually equal to x squared, so now I say x squared is equal to -3 and x squared is equal to -4, which I can square root both sides of all of those and get x equals plus or minus 3i and x equals plus or minus 2i, root 3i. Okay, maybe you liked that technique, maybe you didn't. Maybe you're like, well, Mr. G, why did we just substitute into a different variable? That was kind of confusing. So if that was confusing, let me show you something else. If you didn't like that technique, we can simply state that when you see situations like this, x to the fourth x squared, you are simply allowed to factor it as x squared plus 3 and x squared plus 4. When you have the variables x to the fourth and x squared, that means it's really x squared plus 3 and x squared plus 4. You do get to do what multiplies to make 12 that adds to make 7, 3 and 4, but instead of being x, it's actually x squared. That's just something you're allowed to do, but only when the variables are x to the fourth and x squared. You might say, well, how do you know for sure? You can take your x squared plus 3 and your x squared plus 4, and if you FOIL it out, so FOIL first would be x to the fourth, outer 4x squared, inner 3x squared, last 12, and that gives us back x to the fourth plus 7x squared plus 12. So you can always check by FOIL that it really is true. In any case, this is just, I guess what you could call it is just another trick in your bag of tools of factoring. This is just one more type of factoring technique that you can use. Okay, so regardless of if you didn't like the substitution technique, you can forget about it. You can just know that that's a technique you can use. And so now, once again, we use the zero product rule to finish solving this thing. We want to know, when would that polynomial be equal to 0? Well, when either x minus 1 is equal to 0, or when x squared plus 3 is equal to 0, or when x squared plus 4 is equal to 0. And given those three possibilities, we go ahead and solve. Either x equals 1, or moving the 3 over, you'd have x squared equals -3. And if you square root both sides, you get x equals plus or minus root 3i. And then here, if you move the 4 over, you have x squared equals -4. And if you square root both sides, you get x equals plus or minus 2i. You'll notice now we have 5 solutions. If you wrote them out in a list, it would be your solutions for x are 1, root 3i, negative root 3i, 2i, and negative 2i. Keep in mind in the computer program, it probably wants you to put the I in front of the root 3 so that it's not ambiguous as to whether or not the I is under the square root or not under the square root. You might want to put the I in front. That's the typical standard. So now, how do we write this down as an actual factored form equation? You would write down f of x equals all 5 of your parentheses. And then you start them all off by writing x minus, x minus, x minus, x minus, x minus. And then you just drop in all of those numbers. So one of your x-intercepts is 1, and then I root 3, and negative I root 3, and 2i, and negative 2i. You might be wondering, why do I start it off by making a bunch of parentheses with x minus, x minus, x minus? Why do I start off with x minus? Because keep in mind, if the x-intercept is positive 1, what does the factor have to be? X minus 1. So you can just immediately set up all of your factors by writing x minus, because that's changing the sign from the x-intercept that you actually have. So what's our, if I can go through and get rid of those double negatives, my actual polynomial then is x minus 1, x minus I root 3, x plus I root 3, x minus 2i, and x plus 2i. And that is the fundamental theorem of algebra, that if you start with a polynomial such as x to the 5th, it is possible to factor it into 5 parentheses. If it's a real number, then that represents an x-intercept. If it's an imaginary number, it's not an x-intercept. So this polynomial, this expression here is equal to the original expression, and it represents a polynomial graph that only has a single x-intercept at 1. And it's an odd-powered function, so the end behavior looks like this, and you end up just getting a slight, wiggle there, but only one x-intercept. And that is essentially everything that we get to learn in this class about factoring polynomials. Questions or thoughts? There's a couple more problems but they'll be much easier compared to this process. Okay, well, I know you have at least a couple of those in your homework, so if you have any questions about it, please email me. Otherwise, let's finish these last couple of problems. Everyone, you can cross out number, what, 13? The last 2 problems ask us to write a polynomial with certain characteristics. And we just have one thing left to learn, which is something we noticed from the problem that we just did, and that is, you might want to make a little star note it. Imaginary roots or solutions, always come in conjugate pairs. So, knowing that, just like in the problem we just saw, recall, you had the roots x minus 1, and then you had x minus I root 3, and you had x plus I root 3. So those are conjugate pairs, x minus I root 3 and x plus I root 3. You also had x minus 2i and x plus 2i. So again, those are conjugate pairs. Imaginary solutions always come in pairs. You would never have a polynomial where you had, say, x plus 2i, but then you didn't have x minus 2i as well. So they have to come in pairs. So in this particular one, let's see, the leading coefficient is 1, degree is 5, and we have zeros of I, 6 minus I, and it goes through the origin, which means we know it goes to the point 0 is 0. How do we start this problem? What's the first thing we should write down given all that information? What equation? I would start with the degree 5 bit. I would say, well, if it's degree 5, that means that my polynomial must either look like this, x to the 5th plus something, or I know that my polynomial looks like this with 5 factors. Right? That way we at least have the structure of our answer. Now that I've used the degree 5 bit, I also can use my coefficient of 1 bit. So that means my first coefficient is a 1, which also means there's a 1 out front. So now I've used that piece of information. What piece of information should we use next? Yeah, maybe the origin. Because I know if it goes to the origin that I have an x-intercept at 0. And if I have an x-intercept at 0, that means one of my factors must be x minus 0. So I can go ahead and now call this one x minus 0. So now I've used that piece of information. So the last two pieces of information they have for us is the fact that the zeros are I and 6 minus I. Again, what does 0 mean? Zeros is another word for x-intercepts or roots. So zeros, roots, x-intercept, they all mean the same thing. So if one of my roots is I, now let's try this again, folks. X minus, x minus, x minus, x minus. Because now it's just a matter of plugging in all the rest of my x-intercepts. One of them is I, so what must the other one be? That'd be negative I, which is going to end up being x minus I and x plus I, because they always come in conjugate pairs. So that uses that piece of information. And then one of my other roots is 6 minus I, so I'm going to go ahead and put in 6 minus I as one of them. And then the conjugate of 6 minus I is 6 plus I. And now we've used that piece of information. So that was building the polynomial given the information they gave us. Now we can clean it up quite a bit. We can say f of x is equal to 1, that's just x, and I have x minus I, x plus I, and then we have x, well, we could just leave it like that, but if I went ahead and distributed the minuses, then I'd have x minus 6 plus I, and x minus 6 minus I. And that's the end of our polynomial. Oh, and it even says leave in factored form. So we do not now have to FOIL that all together. We can just leave it like that. And that's the final answer. That was pretty similar to building polynomials like we did before, except this time we have imaginary solutions. And the key to remember about imaginary solutions is that the imaginary roots always come in conjugate pairs. By the way, how do we know that the conjugate of I is negative I? Because we're used to things like 2 plus 3i is the conjugate of 2 minus 3i. So how can I think about the number I? This is really what? 0 plus 1i. Like to write it as a complex number, a plus bi, we can think of I as really 0 plus 1i. So the conjugate of that would be 0 minus 1i. And that gives us just I, the negative I. So those really are conjugates. Just like 2 plus 3i and 2 minus 3i are conjugates. Okay, let's try the last one, folks. Degree 3 polynomial with coefficient of x cubed equal to 1, and then those zeros. Give it a shot, write it down. Just in case you weren't already doing so, I'd start by writing f of x equals, how many parentheses? 3. So you could also start by writing down x minus, x minus, x minus. And then it's just a matter of dropping those x-intercepts into your formula. So we have x minus -4 and x minus -2i and x minus 2i. And it said the leading coefficient was a 1. And so all we have to do is clean that up and say f of x equals 1, x plus 4, x plus 2i, and x minus 2i. You know, one fun little experiment I haven't done is I wonder, can Desmos graph that? Do you think Desmos is sophisticated enough to accept an imaginary number? What is it? X plus 4, x minus 2i, and x plus 2i? No, it is not. Desmos does not understand imaginary numbers. So if I ask it to graph that, it doesn't know what to do. On the other hand, what can I do with my x plus 2i, x minus 2i? I could multiply that together, in which case I'd have FOIL, first x squared, outer minus 2ix, inner plus 2ix, and then last minus 4i squared. Notice the 2ix's cancel out, and then I squared is -1, so -1 times -4 is +4. That's actually just x squared plus 4. So now my polynomial is x plus 4 and x squared plus 4. And that Desmos can graph. Now that I multiplied together my two imaginary roots, I go back over to Desmos, and I can graph that. And wait, do I need to get rid of that f of x? Aha! There we go. And what do you notice about it? How many x-intercepts does it have? Just the one at -4. And you'll notice that wiggle was shoved way out of the way. That wiggle was shifted up quite a bit. What would happen if I shift that wiggle down by about 15 units? Then I would end up having some x-intercepts. And now this would have 3 x-intercepts. And now I could multiply all that out and refactor it into 3 normal factors without any imaginary factors at all. All right, well, we're done with chapter 3, folks, right? Aren't we? Yeah, we are. So I have just a couple minutes here to introduce chapter 4, and then we'll take our break. So recall on the first day of chapter 3-4, I said chapter 3 is all about polynomials. And now you know more than you ever thought you might want to know about polynomials and how to factor them into x-intercepts and how to find the n behavior and the y-intercept and imaginary solutions and synthetic division. And whoo! So exciting, you just know so much about it. Now, chapter 4 is about a rational function. Now, rational functions, it's just a fraction of 2 polynomials. That's it. So when we talk about rational functions, we just mean take 2 polynomials and set one over the other as a fraction. Now, what does that behavior look like? And I'd like to point out the behavior of a rational function as opposed to the behavior of a polynomial function. So just to recap, what's the behavior of a polynomial function? Well, a polynomial function, you really have 2 possibilities. You either have the n behavior that looks like this, or the n behavior that looks like this. Right? That's it. Those are your polynomials. And then the wiggles are either above the x-axis, or they actually hit the x-axis. Likewise for here, you could have no wiggles hitting, well, 1 wiggle, or you could have all the wiggles hitting. So that's basically it for polynomial functions. You've got 2 types of n behavior and wiggles that either touch the x-intercept or not. If they do touch the x-intercept, all of your x-intercepts are real numbers. If they don't touch the x-axis, your x-intercepts are imaginary numbers. And that's it. That's all polynomial theory we just did. So now when we talk about moving on, oh my gosh, I didn't arrange my board. Now when we talk about doing rational functions, what could our graphs look like? What will they look like? Will there be end behavior? Will there be wiggles? What does a rational function look like? Because we just spent a lot of time understanding what polynomial graphs look like. So what does a rational graph look like? The one I'd like to suggest to us as the easiest polynomial graph to think about is not that one. The easiest the easiest rational function to think about is 1 over x. Right? That's just the polynomial 1, and that's just the polynomial x. What does that graph look like? So everyone, let's take a look at what that graph looks like. If you just wanted to think about the easiest rational function there is, it's this. So can everyone see that graph? There. What does that look like? What does it look like? Like with polynomials, you say, well, there's end behavior and some wiggles. That's what a polynomial graph looks like. End behavior and some wiggles. What does that look like?
They're close to 0, but they never touch the.
Oh, very good. You're talking about the asymptotes. Right, there are asymptotes in this graph. There's actually a lot of asymptotes in this graph. Where are all the asymptotes?
In between the areas.
Yeah, anytime the graph is getting closer and closer and closer to the axis but never touched, you have an asymptote. So in fact, how many asymptotes are there? There's 4 asymptotes. You've got this asymptote, and by the way, it's asymptote. If you wanted to be funny at a party, you'd say asymptote. But there's a P in there. We all just say asymptote, asymptote, and it's a silent P. But it's funnier if you say asymptote. Because people will hear it. They're like, did you just say asymptote? You're like, no, I said asymptote. But then throw the P in there again. You're like, asymptote. All right, so you've got one asymptote here. You've got another asymptote here. You've got another asymptote here. And you've got another asymptote here. What's the fundamental feature of a rational function? Asymptotes. Asymptotes. So do you all know what I mean by an asymptote? So you can see that this guy is getting closer and closer and closer, but it never actually lands on the x-axis. And then going up, it gets closer and closer and closer to the y-axis, but it never touches. And then moving to the left, it gets closer and closer and closer, but it never touches. And going down, closer and closer and closer, but it never touches. Yeah, Austin?
If it never touches, where does it stay then? You know?
It just gets smaller and smaller and smaller forever.
Never hits 0.
Yeah, it never hits 0. Yeah, it just gets smaller and smaller and smaller and smaller and smaller forever. In all directions. So all of those are asymptotes. And it will get closer and closer, but it will never touch. So you could say it's getting infinitely close. Yeah. Furthermore, folks, is there an x-intercept?
No.
Is there a y-intercept? No, not on this particular graph. Not on this particular graph. It's just asymptotes all the way around. Now, there's one thing I'd like you to notice. And what is division by 0? Like, if I just type in 1 divided by 0, what will my computer tell me?
Undefined.
Undefined. But we can actually think about what 1 divided by 0 is. Because if you'll notice, look at my table of values. Let's say I do a table of values here, and I start plugging in numbers starting at 5, 4, 3, 2, 1, and then I start doing decimals. So everybody take a look. If I start with 1 divided by 5, that's just 0.2. And then I do 1 divided by 4, that's 0.25. 1 divided by, 3, that's 0.323. Divided by 2, that's 0.5. Divided by 1, that's 1. What happens? Can everyone see this number right here? It's very hard to see, but can you see it? Okay, that's the result of the division. Let's say I start dividing by numbers that are getting closer and closer and closer to 0. Okay, and I want us to see how dividing by numbers that are smaller and smaller creates this asymptote. So what if I divide by 0.1? Then what's my answer? 10. What if I divide by 0.01? The answer is 100. What if I divide by 0.001? Then it's 1,000. Now notice, I'm dividing by numbers that are getting closer and closer and closer to 0. Okay, 0.001 is not 0, but it's close to 0. 0.0001. That's really tiny. It's not even a penny. And yet, when I do 1 divided by that really small number, I get 10,000. So what happens is I keep dividing by really, really, really small numbers. What's the answer? A really, really big number. And that's why this graph is shooting up. It's shooting up really tall and really high and really tall, really fast, because I'm dividing by really small numbers. So if you wanted to say, what is 1 divided by 0? Well, first of all, we know it's undefined. It's an error. You type it into your calculator, it's an error message. But what's 1 divided by 0.00000000? If I were to say what's 1 divided by 0.00000, you would say the answer is a really big number. Right? So if I did 1 divided by 0.00000, the smallest number that you can possibly think of, what would the answer be? The biggest number you can possibly think of. So sometimes just for fun, in terms of being casual, and not accurate, but casual, you might say that 1 divided by a number very close to 0 is the number really close to infinity. And so sometimes you'll see people say 1 divided by 0 is infinity. That's not correct. It's not accurate, and it's not true. Well, what they're saying is if you do 1 divided by a really small number, it equals a really big number. And so that 1 divided by 0, which is close to infinity, is what's causing these asymptotes, this function to shoot up really, really, really tall. But technically, there is no point at 1 divided by 0. Like if I did a table of values and I put 0.001 right here, that would be 1,000. Whereas if I put 0 here, that would be undefined. So there is technically no coordinate on that vertical axis. There's no coordinate anywhere. Okay, well, I think that's enough just to introduce the idea that rational functions, the characteristic feature of a rational function graph is asymptotes. And we'll take a break and then come back and talk about that some more. So the time is 9:01. Let's all be back at 10:01. No, not 10:01. Thank you for, okay, 9:11. There we go. That's a lot better. There are no hour-long breaks in here. I didn't yet, but I told my wife all about it, and so we're gonna drink it together. Yeah, but I'm really excited. She was excited too. She was like, "How did Andrew know about coconuts?" So what's your background that you like coconuts? Is it something your family does, or just something? So you tried it based on his recommendation.
Yeah.
Okay. Okay, cool. Yeah, my wife and I were just doing a bunch of cooking in the kitchen last night. I was like, "Honey, did you notice I have a coconut on the shelf?" She's like, "Oh yeah, I did notice. I've been meaning to ask you." So we talked about it. We'll try it out this week.
Did she like them? Did she ever have?
Oh yeah, she loves coconut water. She's never had a coconut. Yeah. Yeah, which one?
No, the same one.
The one on the computer?
They're solid again. So
Well, pull it up. Let's look at it right now.
my computer died out.
Oh, okay. Well, then, yeah, just write me about it.
Yeah.
Well, actually, we can pull it up on my computer. What number was it?
It was number, I think it was either 12.
Okay. Number 12. So let's look. Oh, yeah, sure. You can.
Just
Actually, I just got an email that the internet is down, which is ironic. If they send out an email telling everyone the internet is down, how do they think people are going to get the email? Right? That's kind of funny. But yeah, apparently everything just went down. That's unfortunate. Oh no, that means I can't even use my Desmos.
that's what I'm saying.
Oh, no, Desmos still works.
Okay.
How curious. But this doesn't work.
You want a program, you can't get it. That's all right.
Yeah, so we'll do it after class maybe.
No, that's all right. Don't worry.
Hey, I was going to go run and get everybody's practice test. I'll be back. All right, folks, it's 9:11. Come on back, folks. All right. Still waiting on a few people.
Take a work on that. Does that make sense? Does that make sense? Yeah, that's what I.
All right, folks. So as we start chapter 4, we're talking about rational functions. As I just said, the main characteristic feature of a rational function are the asymptotes. The asymptotes are what make rational functions rational functions. So everyone please take out your packet called mat150 Properties of Rational Functions. We're going to have a little introduction to rational functions. Okay, yeah. And what I'd like us to keep in mind is that what we're going to do with rational functions is the same as what we were doing with any function, which is find various features of the graph. And two features we've talked about a lot are y-intercepts and x-intercepts. So keep in mind, how do we find y-intercepts and x-intercepts of any given graph? Like for instance, if I just had this graph right here, how do I find the y-intercept? Yeah, you just plug in 0, right? So f of 0. And then how do I find the x-intercept? Yeah, you set f of x equal to 0. So same as before, if you want to find the y-intercept of a rational function, you're just going to plug in 0 into the function, and that will tell you the y-intercept. And if you want the x-intercepts, you set the rational function equal to 0, and you solve for x. So we already know those two answers right there. That for a rational function, if you want the y-intercept, plug in 0. If you want the x-intercepts, set the function equal to 0, solve for x. What we want to do now is find the vertical asymptotes and the horizontal asymptotes. So everybody, take a look at this picture that I gave you right here. I said consider the rational function, and that is a graph of this rational function right here. So I have a polynomial x squared plus 2x minus 3 on top, a polynomial x squared minus 2x minus 15 on bottom. That's a rational function because it's a fraction of two polynomials. Now, taking a look at the graph, which I provided to all of you, the first thing I'd like us to do to continue this idea of what are we going to do for the rest of chapter 4, find the y-intercepts, find the x-intercepts, find the vertical asymptotes, and find the horizontal asymptotes. So what's the vertical asymptote? Everybody, take a look. You can see the vertical asymptote right here. It's at the number 5. Put in a dashed line right there. And call that your vertical asymptote. Asymptote. Right? And what is the equation for that vertical asymptote? It's a vertical line, so the equation is x equals the x-intercept. So it's a vertical line, which is x equals the x-intercept, which therefore is x equals 5. So there, we just found the equation of the vertical asymptote for that graph. Now, what about the horizontal asymptote? You can, by looking at this graph, you can see you have a horizontal asymptote. It's coming down. Well, how far down is it going to go? It's not always going to go down and approach the x-axis. This particular one, you've got a graph coming up, and it's approaching some asymptote, and it's coming down, and it's approaching some asymptote, and the asymptote is actually going to be the dotted line that both of them are approaching. So the bottom one is coming up to the asymptote, the top one is coming down to the asymptote, so the asymptote appears to be in there somewhere. What actual number is that? Let me see here. I'd have to do some scratch work real quick. That's going to be x plus 3x. Oh, no, it's just 1. Yeah, so that's at 1. So everybody put a little tick mark there, call that 1. And so now this horizontal asymptote is a horizontal line. And therefore, the equation is y equals the y-intercept, which in this particular case is 1. So just looking at these two, or looking at this graph of that rational function, we've now identified the vertical asymptote at x equals 5, the horizontal asymptote at x equals 1. And if we could zoom in a little bit, we'd also be able to find the y-intercept, which appears to be right around there, and the x-intercept, which appears to be right around there. Just by looking at the graph, we can't really tell what that is yet. But that's what we want to do. Generally speaking, for the rest of chapter 4, we want to be able to look at a rational function, either the equation itself or the graph, and identify the y-intercept, x-intercept, vertical asymptote, and horizontal asymptote. And so keep in mind, vertical asymptotes are always going to be a vertical line, and a horizontal asymptote is going to typically be a horizontal line. And our graphs are almost always going to look like this. I call this a classic starburst shape. Like, can you imagine, like, especially in December where they show, like, manger scenes and there's a star in the sky? Have you ever seen a star in the sky that looks like that? That's a terrible drawing. I'm not a drawer. But do you know what I'm talking about, how that looks like a starburst? Okay, well, that's what these graphs look like to me. Well, it's not all of the starburst. You'll notice it's just that part and that part. But still, to me, when I look at that, I think, well, I can kind of fill that in and think, okay, it looks like a starburst. Well, anyway, that's the shape. Yes?
There is that asymptote.
There is the possibility of a slant asymptote, yes, and we'll get to that. All right, so folks, let's start big picture and talk about rational functions. So consider this rational function. The graph is shown at the right, tracing the vertical asymptote at x equals 5. You already did. And notice that there's a hole at -3. We already talked about holes, right? We talked about how a hole can show up in a graph. Maybe we did, maybe we didn't. Didn't we? Very briefly. It wasn't very much. We can say we didn't. But notice in this graph there is a hole. So notice I put a teeny little hole in the graph right there, meaning that if I were to plug -3 into this function, it would be undefined. That's what a hole is. A hole means that it's undefined. So why does this graph have the properties shown? As in, which properties? The properties of the asymptotes and the property of the hole. I realize I'm just throwing in the idea of a hole right now. But those are the two features that rational functions have. They have asymptotes and they have holes. Now, when you talk about asymptotes and holes, it's important that you don't abbreviate too much. Right? Like if you're going to be like, what do rational functions have? Asymptotes and holes. Don't just write it out short like that. That could be misleading. It's asymptotes and holes. So why does it have the property shown? Because of the denominator. Right? The denominator is responsible for creating asymptotes and holes. After all, that's really the only new thing that we've created here. If I take away the denominator, what are we looking at? Just a polynomial, which we've already studied. So we introduced a denominator, and by introducing a denominator, we have introduced asymptotes and holes. So the denominator is completely responsible for the graphical feature of a vertical asymptote or a hole. So first, the most important observation about a rational function is this: because there are variables in the denominator could equal 0 if you plug in the right input. So if I plug in just the right number, that whole denominator will equal 0. And if the denominator equals 0, what does that mean? It's undefined. And when a numerical computation is undefined, what does it look like on a graph? It looks like either an asymptote or a hole. So anytime a function ends up with a 0 in the denominator, what you see on the graph is an asymptote or a hole. So, however, as a basic rule in mathematics, we're never allowed to divide by 0. And why not? Well, because it's undefined, but also graphically, it creates asymptotes and it creates holes. So, thus, we perform 3 steps with the denominator of any rational function. So, whenever you look at a rational function, you're going to do these 3 things. First, you're going to find the domain. That is, values of x that you can and cannot plug into the function. And you already remember how to do this. Domain, you only have to worry about dividing by 0 or square rooting a negative. We don't have any square roots in this, so we're only worried about dividing by 0. And so you find the domain just like you did before. You set the denominator not equal to 0, and you solve for those values of x. The next thing you do is find any holes in the graph. And we're going to get into concrete, I'm not going to read the rest of that sentence, but you're going to find any holes, and then you're going to find any asymptotes. So essentially, that's the main thing we're doing, is analyzing the denominator. Because when you find the domain, you're finding the numbers you can't plug into the denominator, and those numbers that you can't plug into the denominator are either going to be asymptotes or holes. And we're going to talk about how to figure out which is which. So with rational functions, you're finding asymptotes and holes. Okay, so down at the bottom, let's go ahead and start practicing that. First, how do we find the domain?
Equate everything the denominator.
What's that, Annabelle?
Equate the denominator to equal to 0 or not equal to 0.
Correct.
And then factor it out.
Yes, correct. So first of all, the domain is defined to be all real numbers except those that cause you to divide by 0 or square root a negative. Oh, maybe that's what I wanted to. Oh, that's what I meant to put on this second line. The first line I was going to say, the domain is defined to be all possible inputs, right? That's the original definition of domain. So I have these two switched. Sorry. The domain is always all possible inputs. And what are you not allowed to input? An input that would cause you to divide by 0 or square root a negative. We don't have to worry about square rooting negatives in rational functions. We won't deal with imaginary numbers at all. We're just talking about dividing by 0. So thus, our job is to find out when the denominator is equal to 0. So to do this, we usually have to factor. So was that the denominator right there? X squared minus 2x minus 15. So we want to know when is that denominator going to equal 0? So I already did it for you. Let me pull that down. I already did that for you. You factor, use the zero product rule, and you say x equals 5 or x equals -3. So I already did that for you. It's right there just to look at. Since plugging 5 or -3 into the function will make the denominator equal 0, we have to exclude the values of 5 and -3 from the domain. Now, first things first, I want you to convince yourself. What happens if I take the denominator, x squared minus 2x minus 15? What was the numerator? X squared plus 2x minus 3. So this is the function we're talking about. What happens if I plug 5 into that denominator? What if I plug 5 in? 5 squared is 25. 2 times 5 is 10. And then minus 15. What's 25 minus 10 minus 15? 0. So definitely plugging in 5 will make it equal 0, which is a no-no. What about if I plug in -3? -3 squared is 9. -2 times -3 is 6. And minus 15, what's 9 plus 6 minus 15? Also 0. So either way, we know for sure you can't plug in 5 and -3 because it will cause the denominator to be 0. So the domain of the function is all real numbers except 5 and -3. We write this in set notation by saying the domain is all real numbers except for 5 and -3. Or you can write it in interval notation as from -infinity to -3, and then again from -3 to 5, and again from 5 to infinity. So I did all that for you just so you can see and follow along. The first thing you do is find the domain. So let's turn the page. Right? Yeah, we have to turn the page. So we know that 5 and -3 cause a problem. Now go back and look at the graph. What do we know 5 to be? 5 is the vertical asymptote, and -3 is the hole. So why is that? That's what we want to figure out. Why is it that one of them caused an asymptote and the other one caused a hole? So, find any holes in the graph. In order to find the holes in the asymptotes in a rational function, you first have to completely factor the original function. So we started with this, and notice I went ahead and did it for you. I factored the top and I factored the bottom. You do a lot of factoring with rational functions. So I factored it. What can we do? Just looking at it, what can we do? You can cancel out that +3, right? So once a rational function is factored, we are allowed to cancel any binomial terms that are in both the numerator and the denominator. And by definition, all right, the whole is represented by the binomial that you cancel. Thus, the term x plus 3 represents the whole. So if you cancel a binomial from the top and the bottom, that's the whole. We could go deeper down the rabbit hole and talk about why that's the whole. But for the sake of time, let's memorize by definition that when you factor in the numerator and denominator and cancel a term, that's the whole. So, and remember, if x plus 3 is the factor, what's the actual location of the whole? -3. So there's a hole for the x. That doesn't make it an x-intercept. We're just saying there's a hole at -3. So -3 is the location of the hole. Meaning, if I did a table of values now with that function, and I plugged in -3, the answer would be undefined. Meaning there's a hole there. There's no actual value. There's no dot on the graph. It's a hole in the graph. Okay, so that's one thing. That's just the definition. If you factor a rational function and cancel a term from the top and bottom, that is the whole. Okay, then find any asymptotes. By definition, the asymptote is given by any binomials that you cannot cancel from the top and bottom. Thus, after canceling the x plus 3, we have this. Right? And I showed it to you right here. Everyone follow along. You've got your rational function. You factored it. You canceled out the x plus 3's. Therefore, that's the whole. And then the term that remains in the denominator is the vertical asymptote, which from now on, maybe we can just call that VA for vertical asymptote. So back up to here, after canceling the x plus 3, we have x minus 1 over x minus 5. We are stuck with the x minus 5 in the denominator. The x minus 5 is important because remember, this could equal 0. What would I have to plug in for x to make that equal 0? 5. So 5 is a number I'm not allowed to plug in because if I plugged in 5, just for instance, if I plug in 5, I get 4 over 0. And that's undefined. And in this particular case, that's creating a vertical asymptote. So we're stuck with the x minus 5. That represents the asymptote. And since it's x minus 5, the actual asymptote is at x equals +5. Okay? These are the definitions, folks. So let's look at our conclusion. When we look at a rational function and you factor it, whatever you cancel from the bottom is the whole. Whatever you don't cancel from the bottom is the vertical asymptote. So however you want to write that down, that's the definition. Whatever terms you cancel, those are wholes. Whatever terms you don't cancel, it's the vertical asymptote. Again, we're only looking at the denominator. The numerator doesn't matter. Is the numerator allowed to equal 0? The numerator is allowed to equal 0 all day long. If I have the fraction 0 over 9, that's just 0. There's nothing wrong with that. You can calculate with 0 in the numerator. You can't calculate with 0 in the denominator. So all of this was focused on the denominator of a rational function. Okay. All right. So, sorry, let me move this up so I can actually look here. So this was my whole. This is my vertical asymptote. So the domain is all real numbers except those inputs that make the denominator equal to 0. So therefore, the domain is anything except 5 and negative 3. The wholes are given by the binomials that cancel. So the whole was at negative 3. And the asymptotes are given by the binomials that don't cancel. And so my asymptote is 5. Okay, so that's it. I mean, that's not it. There's still a lot more to learn about rational functions. But that's the primary ideas right there, is that rational functions are unique because they have denominators. Denominators can't equal 0. If denominators do equal 0, it creates asymptotes and wholes. The wholes are the binomials that do cancel. The asymptotes are the binomials that don't cancel from the denominator.
Can you solve for the, if you equate x minus 1 to 0, isn't that also solving for your horizontal asymptote?
Not horizontal asymptote. Do you mean x-intercept?
X-intercept.
Yeah. So now that we have that x minus 1 and over x minus 5, you take that and set it equal to 0 and solve for x. You can do that. So notice x minus 1 over x minus 5, set it equal to 0. That will find the x-intercept. What can we do if we want to solve for x? The first thing we could do is multiply the denominator off to the other side. If I multiply both sides by x minus 5, over here it cancels them. So you just have x minus 1. And over here, 0 times anything is 0. And so now you just have x equals 1. So it turns out the x-intercept is just 1. And folks, if you go back and look at the original graph, go back and look at the original graph. Where's the x-intercept?
That's why I was asking that question.
Yeah, if you look at the graph, the original x-intercept is at 1. You can almost kind of tell. The graph is very badly photocopied. But the x-intercept is indeed at 1. Okay, let's turn to the next page. So rational functions continue. So thus far, we've only considered the denominator of a rational function. The denominator is what's new. The denominator is what causes asymptotes and wholes. But we want to be able to solve the entire rational function. And so these are all the questions that we would ask. The denominator of a rational function is especially important because it might equal 0. What about the numerator? So what can we learn from the numerator? What about the fraction as a whole? What can we learn from that? Right, so far we've only looked at the denominator causing asymptotes and wholes. What information do we get from the numerator and what do we get from the whole fraction? In general, we might want to ask these questions. the y-intercept was really hard to tell on this graph, but do you believe that that's 0.2? I mean, do you buy it? It's true. If we did it on Desmos, that's what we would do. So, what is the y-intercept? The answer is plug in 0. That's your technique. What about the x-intercept? We'll move this down a little bit. No, we'll move it up. There we go. So what's the x-intercept? What does every x-intercept have in common? Again, this is just the chain of reasoning. This x-intercept would be 3, 0. And this x-intercept would be 5, 0. What does every x-intercept have in common? Y equals 0. So y equals 0. Thus, every x-intercept has the form some number, comma, 0. Thus, for every x-intercept, the y-coordinate is always equal to 0. Thus tells you that if you want to find the x-intercept, let y equal 0. Again, this is just a chain of reasoning to remind you. How do I find x-intercepts? Let y equal 0. Therefore, set the entire function equal to 0. So now if I take this entire function, maybe write down f of x equals. That was our function. And I'm going to take that whole thing and set it equal to 0. And solve. This is our technique for finding the x-intercepts. Just set the whole function equal to 0. What can we immediately do to the denominator? Just like I did a second ago.
Don't you want to factor out?
Even before we factor anything. Yeah. What? Cover it? Oh, well, I mean, you could cover it. Wait, did you mean this way or this way? I like the idea of covering it. But let's be mathematically precise first. What are we going to do?
Cancel.
How do you cancel it? Multiplying both sides by the denominator. If you multiply both sides by the denominator, so x squared minus 2x minus 15, and over here x squared minus 2x minus 15. If I multiply both sides by the denominator, first of all, it cancels the denominator on the left. And maybe, Jose, that's what you meant by cover it. And maybe that's what you meant by cancel it. And what's 0 times that whole thing is still just 0. So what we end up with is x squared plus 2x minus 3 equals 0. So for any rational function, if you want to find the x-intercepts, you don't have to set the whole function equal to 0. What are you really setting equal to 0? Just the numerator. And that's your technique. Set the numerator equal to 0 and solve for x. So now that I have my numerator equal to 0, I factor it. That's x plus 3, x minus 1. And I use the 0 product rule. That means either x plus 3 equals 0, or x minus 1 equals 0, which means x equals negative 3, or x equals 1. Those are my possible x-intercepts. Those are my possible x-intercepts. Technically, that is where technically that's where the function is equal to 0, which would technically be an x-intercept. However, remember, what was x equals negative 3 equal to? A whole. So it can't possibly be an x-intercept because it's a whole. Okay, so that's it for x-intercepts. If you want the x-intercepts, you set the numerator equal to 0, and you solve. Oh, now, Annabelle, you said, wouldn't you first want to factor? Now, that's a really good point, because if you first factored, you'd have a lot less to set equal to 0. Yeah, so that's a good point, Annabelle. I suppose you could go ahead and take care of factoring the top and the bottom and simplifying and canceling any holes first, and then doing the work. That's a really good point. Okay, next, where are the vertical asymptotes? Do we have to turn the page? Or are you still on the same page? So the vertical asymptotes we already talked about. So how do we find the vertical asymptotes and or the holes? We already know the answer to this. You'll have vertical asymptotes whenever. So first you'd have to factor. So that was x plus 3, x minus 1. And that was x plus 3, x minus 5.
Yeah.
Yeah, so then those cancel out. You just have x minus 1 over x minus 5. This was the hole. This was the vertical asymptote. So you'll have a vertical asymptote whenever a binomial in the denominator does not cancel out. Whichever binomials do cancel out are poles, whichever binomials don't cancel out are vertical asymptotes. And then just as a bonus question for you to consider is to wonder why. We won't talk about that right now. I want you to play with the idea. Why is it? Well, we had kind of already talked about it at the beginning. Dividing by numbers closer and closer to 0. The answer is a number bigger and bigger. So that's just a question for you to think about. All right, so that's where the vertical asymptote is. And since it was x minus 5 in the bottom, you set x minus 5 equals 0, which gives you x equals 5, and therefore that is the vertical asymptote. Okay, so in other words, the technique, where are the vertical asymptotes? Set the denominator equal to 0. When you set the remaining denominator equal to 0, that gives you the vertical asymptotes. The last feature for us to consider is a horizontal asymptote. And a horizontal asymptote is slightly different in terms of a chain of reasoning and how to think about it. A horizontal asymptote occurs when you go very far to the right or left. So first of all, I just want us to all kind of agree on that idea. That a horizontal asymptote is what happens when you go really, really, really far this way or really, really, really far this way. So essentially, the horizontal asymptote is when you let x equal, like what is x equal to way over here? Infinity, or just something really big. Horizontal asymptotes are what you get when you plug in a really big number for x, either positive or a really big negative value for x. You could just say plug in positive infinity and plug in negative infinity. And that would be kind of true. You could kind of tongue-in-cheek say plug in positive infinity and negative infinity. But you can't really plug infinity into a function. You know, how do you substitute infinity? You can't really. So, in words, as you go really far to the right or left, what does your function approach? So, as you go far to the right, left on a graph, does your function approach a particular value? So in this graph, we saw that the further you go to the right, this function is approaching 1. It's approaching 1, the y value of 1. And as you go really far to the left, this function is approaching the y value of 1. That's a tick mark. It's not negative 1, it's positive 1. So the horizontal asymptote is whatever your graph approaches as you go really far to the right and really far to the left. So to determine what that answer is, we follow a particular process. So here's the process. Take the ratio of the leading terms. So first of all, what does that mean? What's the leading term of x squared plus 2x minus 3? The whole term, not just the leading coefficient, the whole leading term. 1x squared. And what's the leading term of the denominator? 1x squared as well. So the leading terms, those are the leading terms right there. And we take the ratio. So the ratio of 1x squared over 1x squared, what is that ratio? What's 1x squared divided by 1x squared? It's just equal to 1. Well, that was the horizontal asymptote. The horizontal asymptote was 1. So a lot of times that's it. That's how you find the horizontal asymptote. You simply take the ratio of the two leading terms. So whatever the leading terms are, you take that ratio as in fraction, and whatever that equals, that's your horizontal asymptote. However, it's not always going to be that simple. Sometimes, let's just say the leading terms were actually 2x squared over 3x. Well, if you do that, you keep the 2 over the 3, but you're going to have an extra x up in the numerator. So you'd have to do more there. Or perhaps you have 5x over 6x squared. And if you simplify that, you end up with a x in the denominator. So it's not just take the ratio of the leading terms. Rather, you take the ratio of the leading terms and let x equal infinity and negative infinity. Now, you can't really let x equal infinity. you let x become very, very large to the right, or x become very, very large to the left. So for instance, if I now take this fraction, 2x over 3, and I let x become very, very large, what's 2 times a really large number divided by 3? A really large number. So this approaches infinity. As you let x become bigger and bigger and bigger, 2 times a really big number divided by 3 is still a really big number. So this asymptote would actually go to infinity. That's something special. We're going to talk about that in a second. Whereas here, what if I let x become a really big number? Since it's in the denominator, what's 6 times a really big number? A really big number. What's 5 divided by a gigantic number? Like 0.000003 maybe? So this actually approaches 0. Okay, the general idea is you take the ratio of the leading terms and you look what happens when x becomes very big. So in general, we can summarize it and say, if the degree of the numerator is less than the degree of the denominator, let's do an example. If the degree of the numerator is less than the degree of the denominator, like that. So let's say you had x to the 1 over x squared. Then when you simplify it, that would just become 1 over x. And if I plug in a really big number for x, that goes to 0, because 1 divided by a really big number approaches 0. Whereas if the degree of the numerator and the degree of the denominator are the same, like x squared over x squared, then all the x's cancel out, and you're just left with the ratio of the coefficients. And so that just gives you a normal horizontal asymptote. Whereas if the degree of the numerator is bigger than the degree of the denominator, like x cubed over x squared, then you end up with an x left over. That's really x over 1. In which case, that goes to, if you let x become a really, really big number, then you get a really big number. So these are our 3 different scenarios. If the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is at 0. And if the degree of your numerator and the degree of the numerator are the same, then your horizontal asymptote is whatever that ratio is. You know, whatever the ratio of the coefficients was. Whereas if the degree of the numerator is bigger than the degree of the denominator, you technically have something special called a slant asymptote. And we'll talk about that in turn. You know, writing this down, what we really need to see are some examples. And I don't have a ton of examples right here. I really just intended to give you the definition. And so the definition is you take the ratio of the leading terms and you let x become a very large number. So let's take all 4 of these now and summarize everything. How do we analyze a rational function? These are all the steps that you do when looking at a rational function. And of course, what's our end goal? For anything that we ever do with a function, our end goal is to draw a picture. That's really your end goal, right? Your end goal is to draw a graph, which of course you can do just by plugging it into Desmos. But we want to learn all this so that you could draw it yourself without a graphing calculator. So just like polynomials, your end goal is to be able to draw a graph without a graphing calculator, even though you're allowed to use a graphing calculator. So what is the domain? Set denominator not equal to 0 and solve for x. That's your technique to find the domain. You say, set the denominator equal to 0 or not equal to 0, find all those values that would make the denominator equal to 0, and know that you're excluding those values from the domain. Where are the holes? Any binomials that cancel. Where are the asymptotes? Any binomials that don't cancel. What is the y-intercept? Plug in 0. What is the x-intercept? Set the numerator equal to 0 and solve for x. Where are the vertical asymptotes? Set the denominator equal to 0. And solve for x. And what are the horizontal asymptotes? Take the ratio of the leading terms. And let x become very, very large in both the positive and negative direction. That's not really technically accurate to say let x equal infinity. What I mean is let x become a very, very large number, or let x become a very, very large negative number. So this little conclusion sheet that you have right there, I would keep that. Keep it out with you whenever you're looking at this work. Maybe even just cut that little piece off the bottom and tape it to your forehead. Or just keep it with you when you're doing all of your work, because this is a nice, concise list of all the techniques that we're going to do with rational functions. So everything we just did, that packet that you just did, that was just an introductory packet so that I could introduce you to all the main concepts. I'm not going to collect that. That's not for a grade. But now, theoretically, we understand everything there is to know about rational functions. And now we're just going to go do a bunch of examples and see how this plays out in practice. And we still have half an hour. I should remember, but please remind me, I have your practice test right here for chapter 3 and 4. I'll pass that out at the end. All right. Everyone super excited to flip over to the other packet and start doing some examples? Oh, did I turn that too fast? Did everyone finish writing all that down? Did everyone finish? Everyone good? Okay. All right, so, these packets, they give us a bunch of definitions. Sometimes the definitions are good. Sometimes the definitions are a little, I think, worded a little strangely. We can just take a look here. Rational function is any fraction of two polynomials. The domain of a rational function consists of all real numbers, excluding the values that make the denominator equal to 0. So set the denominator equal to 0, solve, and exclude those values from the domain. And then you can see here they talk about vertical and horizontal asymptotes. So a vertical line x equals c where the graph tends toward positive or negative infinity. All right, and then a horizontal line where the graph approaches the line as the inputs get really large. And then how to find the location of vertical asymptotes and holes. I don't necessarily like this definition. I like the definition I gave you. It's really nice. You cancel it, it's a hole. You don't cancel it, it's a vertical asymptote. This is just another definition, which I'm not even going to read to us because I like the definition I just gave you. If you'd like to read it, you can. But in class, we'll be talking about canceling and not canceling. Okay, and then this is a summary of the location of horizontal asymptotes, which we just talked about. If the degree of the numerator is bigger or smaller, we'll do a bunch of examples of those. And then slant asymptotes we'll get to when we do it in practice. So let's just go ahead and skip on past all of these definitions and try some examples. You can always go back and read those yourself. I feel like we just did a lot of work, taking on this whole new idea of a rational function. I feel like I should tell you another joke. I don't know that I have another joke for you. I wonder if I can pull off that other joke. That's another good one that I really like. Oh, I'll tell you one that I've been telling my daughter a lot lately. I'm sure you've already heard it. What is a pirate's favorite letter? R. Yeah, okay, that's it. That's my joke. She loves that one. Okay, so identify the domain of F. How do we identify the domain? We'll go in order here. I'll say A. How do we do the domain? You set the denominator equal to 0. So in this case, we say 3x minus 6. I don't want that to equal 0. That gives us 3x can't equal 6, which means x can't equal 2. So the domain then is just x can't equal 2, which if I did that in a number line, you'd have two intervals. And so your domain would be negative infinity 2 union 2 to infinity. Right? That's how we've already done that in previous chapters. Finding the domain, you just set the denominator not equal to 0, find that value, make a number line, and write the number, write your interval notation. How about B? Identify any vertical asymptotes. Well, did we factor this at all? We can try. This factors into what? X over 3 over x minus 2? Can we cancel anything? No. And therefore, there are no holes. We didn't cancel anything, so there are no holes in this graph. The only binomial that remains must be a vertical asymptote. And therefore, the location of the vertical asymptote is at x minus 2 equals 0, which means x equals 2 is a vertical asymptote. So again, the vertical asymptote is any binomial that remains after you cancel everything. And so we have a vertical asymptote at x equals 2. Oh boy, I just glanced at your paper, and you have a very small amount of space to write all this on. You might want a sheet of lined paper to capture all this. Okay, identify any holes in the graph. Were there any holes? No holes. Because you didn't cancel a binomial. No holes. Okay, D. Find the horizontal asymptote, if it exists. So for the horizontal asymptote, you take the ratio of leading terms. In that case, our ratio is 1x over 3x. Does everyone agree that the leading terms are x and 3x? So you take that ratio, we can cancel out the x's, and we're left with 1/3. Therefore, the horizontal asymptote is at, so the horizontal asymptote is at y equals 1/3. In other words, that's the value that your horizontal asymptote is approaching as you go to the right and as you come up from the left. Now, E, it says find the slant asymptote. A slant asymptote only exists if the degree of the numerator is greater than the degree of the denominator. So there is no slant asymptote. You only get a slant asymptote if you have a fraction like x cubed over x squared. It has to be bigger on top. And that's not what we have here. So there's no slant asymptote. Oh, on if? I meant only if. Only if. And finally, graph the function. So let's try this together. We're going to put down all of our key attributes first. What are our key attributes? Oh, they didn't even have us find the x-intercept, did they? Or the y-intercept. Well, we can do that on the fly. How do you find the y-intercept? You plug in 0. So that's 0 over -6. What's 0 over -6? 0. So the y-intercept is at 0. What's our x-intercept? The x-intercept is when you set the numerator equal to 0. So where's our x-intercept? If you set x equal to 0, it's just x equals 0. So there's really only one intercept. That point right there. Okay, where was our vertical intercept? At 2. So everyone come over to 2 and put a vertical dotted line. So that's where our vertical asymptote is. And then the horizontal asymptote is at 1/3. So you go up on the y-axis to 1/3, and you put in a dashed horizontal line. And so that gives you the location of your vertical asymptote, your horizontal asymptote. And at this point, you make your starburst shape. The starburst shape would be that I have that over here and this over here. Noticing that your starburst shape aligns itself with the asymptotes that you put in with the dotted line. Now, of course, what should we do? We should check that we did that correctly. So I'm gonna, oh no, I wonder if it's still, x over 3x minus 6. How did we do? I'm even going to put in the vertical asymptote. Here's the horizontal asymptote. Is that what our graph looks like? Yeah. So there we have it. We knew enough theory to draw a graph, even though we can just use Desmos to do it for us. At which point, I'm sure you're all saying, exciting. This is awesome. We can take a rational function and graph it without a graphing calculator, even though we are allowed to use a graphing calculator, and that is the whole point. So let's try that again. Let's try that again with this one. Now, folks, what do you notice is strange about this? The polynomials are kind of written backwards. Let's write that forwards. That's actually 7x plus 3 over negative 2x plus 5. Okay, let's try the whole process over again. So find the domain. Domain is, what can't you plug into the denominator? Well, I don't want negative 2x plus 5 to equal 0. So negative 2x shouldn't equal negative 5, which means x shouldn't equal 5 halves, or 2.5. So the only value that we're excluding from our domain is 2.5. If I made a number line at 2.5 and excluded it, then you would see that your interval notation for the domain is negative infinity to negative 2.5. Oh, sorry, positive 2.5. Union 2.5 up to infinity. So that's finding the domain. Again, we've done problems like that in previous chapters. So B, identify any vertical asymptotes. Remember, vertical asymptote is whatever doesn't get canceled out. So when we look at 7x plus 3 over negative 2x plus 5, can we factor either of those? No. And therefore, we can't cancel anything either. So first of all, since we didn't cancel anything, there's no holes. Again, this graph has no holes because no binomials got canceled out. The only binomial that remains is negative 2x plus 5. And therefore, our vertical asymptote is represented by that. So where is the vertical asymptote? You just set that equal to 0, which is the exact same equation we just solved, which means the vertical asymptote is at 5 halves. Those two facts kind of go together. 5 halves is excluded from the domain because it's a vertical asymptote. Asymptotes and holes are not part of the domain. So those two answers are the same because they're talking about the same thing. So there's a vertical asymptote at 5 halves, which means technically the function is undefined right now. Okay, let's see, identify any holes. There were no holes. Find the horizontal asymptote. So once again, we take the ratio of the leading terms. The ratio of leading terms. In this case, that's 7x over negative 2x. The x's cancel out, and you end up with negative 7 halves, which is really negative 3.5. So the horizontal asymptote is at y equals negative 3.5. So we have our vertical asymptote. We have our horizontal asymptote. All of this is helping us to make our graph. E. Now, automatically, if there's a horizontal asymptote, there's no slant asymptote. So we already know the answer to E is that there is no slant asymptote. There's only a slant asymptote if the degree of the numerator is greater than the degree of the denominator. In this case, the degree of the numerator and denominator are the same. The degree of both of them are just degree 1. So there's no slant asymptote, and then finally F. Oh, goody, graph the function. And you'll notice in this particular problem, they don't ask us to find the x-intercept and the y-intercept. So can we draw our graph even if we don't have those pieces of information? Yeah. So take a look. The vertical asymptote is at 5 halves. That's really 2.5. So I go to 1, 2.5. So here's my vertical asymptote. A vertical line at 5 halves, which is 2.5. And then my horizontal asymptote is at negative 3.5. So I go down 1, 2, 3.5. There's my horizontal asymptote. And then we make our starburst shape. Now, right about now, you might be saying, so Mr. G, let me get this straight. We just find the vertical and horizontal asymptote, make a little crosshair on the graph, and then draw in a starburst shape. Yes and no. Sometimes it's just that easy. Other times, that starburst shape might be flipped. So it might be the starburst shape, it's this piece is down here, and this piece is up here, depending on the sign of the overall function. So what should we technically do with every graph we draw? You want to check your work, right? Check to make sure that it actually is correct. So let's go ahead and do that real quick. This was 3 plus 7x. Oh my gosh. Divided by 5 minus 2x. And sure enough, this one was flipped. So checking our work with the graph is kind of important. That starburst shape got flipped. Now you might ask why. Why is it that sometimes the starburst shape is right side up and other times upside down? That's a good question. And ultimately, you answer that question by doing a table of values to get a test point. You do a table of values to get a test point. So let's see what that looks like. If I wanted to know, does my graph look like this, the way I had drawn it? Sorry, everyone, you have to erase. Or is it flipped upside down, and my asymptotes are down here, and one up here? This is what the graph actually looks like, and to figure that out, you just need one test point, at least one test point. And you say, well, let me just make a quick table of values, and I'll just choose one value to plug in and get one coordinate. Because if I have one coordinate up here, then I know that that part of the graph goes up here. But if I get one coordinate down here, I know that part of the graph goes down here. So this was 1, 2. Let's choose the input value of 3 and see what we get. If I plug in 3, I'm about to find the location of my coordinate over here in this region. So if I plug in 3, what do I get? If I plug in 3, that's 7 plus 20. Wait, 3 plus 7 times 3 is 21. Over 5 minus 2 times 3 is 6. And that gives me 24 over negative 1, which is negative 24. Therefore, I know the coordinate 3, negative 24 is on the graph. And the coordinate 3, negative 24 is way down here. And that tells me that that part of the graph goes down here, and the other part of the graph goes up here. Now you might say, Mr. G, that's not a very satisfying answer. How do you know ahead of time? You don't really know ahead of time. Technically, you should always do at least one test point to verify where that graph actually is. But at the very least, we know that it's going to be this starburst shape, either with the piece to the upper right and the lower left, or with the piece to the lower right or the upper left. How do you know for sure? You do a test point. I don't really have a better way of telling you how to know which is which, whether it goes to the upper right or to the lower right. The key is to do at least one test value to nail down where that piece of the graph goes. And of course, just graph it on Desmos and then you can see. All right. Well, those were two straightforward examples. As you can see, the next few get a little more complicated. What makes them more complicated? What makes these next problems look a little more exciting? Because why? Because of the x squared term. Yeah, the x squared term makes these next couple of problems a lot more exciting, right? But what does that presence of the x squared term mean we're going to do? We're just going to factor. And if we factor, that means we might cancel one of those binomials, which means we might get a whole. But otherwise, that's it. It's not really that much more complicated. It just means that you get to factor the expressions, and therefore you might be able to cancel something. All right, let's try number 3. How does that factor? There's still just one x on top, and on bottom, what do you multiply to get 12 that adds to make 1? Is it 4 and 3?
Yes.
So x plus 4, x minus 3. Is that it? Okay. Did we cancel anything? No. Okay, so there's still no holes. But now this is really exciting. Okay. Up until this point, we've been thinking about rational functions in a fairly simplified way, that it's just one starburst shape. You can have more than one vertical asymptote. So in this case, neither of these got canceled. They're both vertical asymptotes. And now the graphs start to get a little more interesting. So let's go ahead and walk through the steps real quick so that we see how to do it. Find the domain. So what can't x equal? Maybe at this point we can just go ahead and, just by looking, what can't x equal? -4 or 3. So x can't equal -4 or 3. Furthermore, neither of those got canceled, so they're both vertical asymptotes. So I already know that my domain exclusion are both vertical asymptotes. That helps me do part B, where they say identify the vertical asymptotes. Those are the vertical asymptotes. So the vertical asymptotes are at x equals -4 and 3. Are there any holes? No holes. Find the horizontal asymptote. Same thing, you take the ratio of the leading terms. The leading term on top was 1x. Leading term on bottom is 1x squared. The ratio of our leading terms are therefore 1x over 1x squared. What happens there? One of the x's cancel, because that's really 1 times x over 1 times x times x. So one of the x's cancel, and we're left with 1 over x. Now, the definition was take the ratio of the leading terms and let x become a very large number. So if x becomes very, very large, that's like 1 over a billion, which is essentially 0. So the horizontal asymptote is going to be y equals 0. Because as I let x become a very, very large number, like 1 divided by a trillion or 1 divided by a quadrillion, you get 0.00000000 something, which is essentially 0. Since there's a horizontal asymptote, there's no slant asymptote. Again, that's only if the degree is bigger in the numerator than the denominator, which was not this case. And now we get to make our graph. So let's start by putting on our vertical asymptotes. The vertical asymptotes were at -1, 2, 3, 4. So there's one dotted line, vertical asymptote. And then another vertical asymptote is at 3, 1, 2, 3, 2, 3. There's our other vertical asymptote. And then our horizontal asymptote was at 0. So I put in another horizontal asymptote there. Okay, so we essentially have this space now where we have, can we all agree that there are 6 regions? This region, this region, this region, this region, this region, and this region. So the presence of the horizontal asymptotes, let me draw it over here. I had 2 vertical asymptotes and 1 horizontal asymptote. That creates 6 regions. 1, 2, 3, 4, 5, 6. And the graph is going to exist in 3 of those regions. You only get, either the top or the bottom. So the graph could be maybe up here, and then maybe here, and then maybe here. That might be what our graph ends up looking like. The key thing is you're going to have a graph in each vertical region, but only either the top or the bottom, either the top or the bottom, either the top or the bottom. So there's a lot of possibilities there. One of the possible graphs that this could look like would be down here, and up there. That could be what the graph ends up looking like. The only thing to do now is to either graph it on Desmos or do a bunch of test values. I'm going to graph it on Desmos so that you can see what this one looks like. This was x over x squared plus x minus 12. So that's what our graph ended up looking like. I'm sorry, I misspoke a little bit. I said that it would either be on the top or the bottom. I'm sorry. One of them could be the top and the bottom, depending on what the graph ends up looking like. Okay, so that's what our graph looks like. Let's sketch that in on your own paper. We have a piece in the lower left, a piece in the upper right, and then in the middle region, it comes down to the right and down. So let's draft that. What did I just say? A piece in the lower left? Was that right? Lower left, upper right, and then this one goes down and down. That's what the graph ended up looking like. there's no way to really predict that. Just like off the top of your head. Like just looking at that function, you would never be like, oh yeah, one in the lower left, one in the upper right, and one in the middle. It goes like this. The only way to know what the graph looks like is to either graph it on Desmos or your graphing calculator or use test values. Yes, Andrew. The one in the middle can, well, first of all, any graph can cross the horizontal asymptote, like in the middle. The horizontal asymptote is only what this piece approaches far out to the right, and what this piece approaches far out to the left. In the middle here, something can cross a horizontal asymptote. The horizontal asymptote is only talking about what happens really far to the right and really far to the left. I don't know if that answers your question. You can cross a horizontal asymptote. The horizontal asymptote is just there to tell you what this piece of the graph is heading towards as you move very far to the right, and what this piece of the graph is heading towards as you go really far to the left. Did that answer your question? Maybe, maybe not. Horizontal asymptotes are about end behavior. That is all the way out to the far right and left.
So that was that one have a
Yeah, this one does actually have an x-intercept. Wherever that would be on the graph, I didn't make note of it over there, but there would be an x-intercept and a y-intercept. Yeah. Now, folks, right about now, you might be saying to yourself, what are we even talking about? What is the purpose of a rational function? What are we even doing? We're finding vertical asymptotes and horizontal asymptotes, and then we're drawing in swoopies? How does this possibly matter? Well, again, in a math class, you look at various types of functions and you look for their behavior, and you try to understand that behavior. And the main behavior we're looking at in this section is vertical and horizontal asymptotes. And the main thing here is not how exactly this swoopies, but the fact that it's contained within two vertical asymptotes. And that that's a vertical asymptote and that's a vertical asymptote. And how you draw that particular part in the middle, well, you know, you can basically just sketch it. The main thing to notice is that there are vertical asymptotes. And again, over here, the main thing to notice is that you've got a vertical asymptote here and a horizontal asymptote here. The fact that it curves, you know, that's just incidental. The main thing we're really talking about are the vertical and horizontal asymptotes. And that's what we're trying to study in this section. Everyone, for fun, you can cross off number 4. I'll make sure a problem like that doesn't show up in the homework. Boy, these next two will be really nice because I'm betting there will be some holes on the graph once we factor those. You don't have to work ahead, folks. I'm kind of wrapping up class right now because it's almost over. You don't have to work ahead, so don't work ahead, but just so you see where we're going, they're going to now give us a bunch of functions which they want us to graph. So we find the y-intercept, x-intercept, vertical and horizontal asymptotes, and maybe slant asymptotes. We're going to practice that in the next class period on what, Wednesday? Of course, you're allowed to use your graphing calculator to confirm, but otherwise we're going to use the tools that we've built. And so we're going to do a bunch of graphing to see what these graphs look like. We're going to build some functions to have particular vertical asymptotes and particular horizontal asymptotes. We're going to solve some just straight up equations that have denominators. And then what else? We'll solve a couple word problems. Okay, so I'm just talking about where we're going. I'll go ahead and tell you that we are going to use our review day to finish part of this. So where's my calendar here? Oh, there we go. So today is October 1st. We have Wednesday, and then the next Monday is a review day. Our lesson is going to continue on to that day, but I'll try to keep us at least, you know, the last 30 minutes of that class to look at the practice test. Okay, so the practice test. Folks, here's your practice test. If you would pass these down to your classmates. Now you'll notice the practice test right in the very top. There's a typo. I call it the test. Chapter 3 and 4. This is not the test. This is the practice test. So everybody, if you would, just up at the very top, will you just handwrite in, please, the word practice so that you or I get confused about the fact that whether or not this is the real test or practice test. This is the practice test. You wouldn't mind that, though? No. Okay, now everyone take a look at the practice test. You'll notice I did this just like the last one. So on the very first page it says test chapters 3 and 4. We start with chapter 3. So I number them 10 problems from chapter 3. So if you flip, you got problems 1 through 10, and then that's the end of chapter 3, and then the next page says chapter 4. And then from chapter 4, I've selected 10 problems, and I number them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and those are 10 problems from chapter 4. So ultimately, after all the work we've done in chapter 3 and 4 and all the homework we've done online, we've got 10 questions from chapter 3, 10 questions from chapter 4, and then of course your real test is going to look almost exactly like this. All right. What questions would anyone like to answer? For instance, did we finish section 4.1? I don't think we did. Oh, but that doesn't matter. This week for sure we'll finish 4.1 and 4.2, so that's going to be your homework due on October 8th. Because I doubt we'll finish 4.3 on Wednesday. So the only homework that's going to be due this upcoming Monday is 4.1 and 4.2. I think that's it. It's 10:19. I don't have anything else to tell you. Anyone has any questions, please come see me. Come to my office hours. Adios. Oh, you're going to give it to him. Very good. Thank you. Oh, you know, I haven't even looked into that. Have you had any absences yet? Oh, right, okay. Oh, but and that was from the surgery? Oh, okay. No, I haven't done anything with regards to. Oh, right, because you were asking about whether or not that would count against it. Thank you for reminding me about that. I have not actually investigated that. So what I'm going to do then is you're going to have surgery, and you're going to miss 2 days.
Yeah, because I'm like.
Right. And because you're missing those 2 days, you know you're going to be able to watch the material because you can watch the video. So you're going to have no problem there.
Yeah.
But the question is, can you not have the consequence from my syllabus? Right. Okay. Let me go talk to my head of department, and I'll ask about that.
Okay.
Okay. And essentially, the only way that's really going to work would be if you brought me like a doctor's note.
Okay.
Something regarding the surgery, something from your doctor letting me know that you did have the surgery,